Okay, may I have your attention, please? We are going to get started. All right, so it's ready? All right, so excuse me. All right, so in fact, I was about to mention that if you want discussions, you should have plenty of that chance with me after class. I start to see first batch of students showing up in my office hours, and I do encourage you to come, which is every Monday right after the class. So feel free to drop by, discuss anything, projects or materials in the classrooms and stuff like that. So today we're going to continue our discussion last time about elimination. And in particular, we're going to also start an extension of elimination algorithm known as belief propagation. This is one of the first algorithms I personally heard about machine learning. It's very famous, very actually deep. And we're going to revisit this topic several times. But today, we're going to have our first encounters. So just to recap a little bit, we used a pretty good chunk of time last class establish this realization that marginalization can be done through something called a algebraic elimination. You just massage the position of the summation sign among all the factors in the product, and then you're going to get some reduction. And then we say that this algebraic elimination can be also captured by a graph elimination in which the elimination was defined by a certain operation, which is to remove nodes and tie together the neighbor of that node and record that intermediate product. So here I have this graph where you can see the intermediate terms resultant from every step of algebraic elimination. And then here I have the graph intermediate product resultant from a graph elimination. And you can see the one-to-one correspondence, right? Each of the factor here correspond to a factor in the algebraic elimination. So what's the utility of that? Well, one utility we mentioned is about now estimating the complexity of this elimination. Here you need to write a lot of equations. If I have a huge graph which contains, say, 100 nodes, you probably have no space to write down this equation and do this stepwise elimination. But you can pretty much do that on a graph, or using the computer program. And here you can also see the biggest term in which you have the most number of variables. But in here you can just establish equivalence of this to the size of the intermediate cliques that you produced. And that one usually defines the bottleneck of the complexity of elimination, right? So we're clear about that. Any question with that? And we did an experiment, an exercise last time already, which showcase two pieces of information, right? One is that you can use the graph to conduct graph elimination and get an assessment of the complexity visually. And secondly, you can also use this to inspire better elimination ordering among all possible different orderings, right? So in this case, you want to peel from the peripheral to the heart instead of starting from the heart and go outward, because otherwise you're going to produce a gigantic clique even in your first step, right? And in this tree one, you don't really have a difference. You can probably actually you also have a difference. You want to peel from the edge, right, to the leaves, to the roots. So now let's just test whether you guys really get the essence of that idea. So let's do another elimination exercise. So here I have a model you know already. It's called the Ising model. Can anybody tell me what is the complexity of this algorithm, of this of inference on this model? I'm talking about the exact. In fact, the question was quite vacuous. So greedy, algorithm. What is the greedy algorithm there? What do you actually do? Let's be very exact about what we mean. Elimination and the inference, computing the marginal of every node in this graphical model. What is the complexity of that? How to start? Maybe we should go with the very first step. What do you do actually in elimination? You need to do elimination anyway, right? So what do you do? Where do you want to start?
Corner.
Okay, let's maybe try a corner idea. In fact, you try other places, roughly give you the same thing, but corner. So let's eliminate this one. What should I do? After eliminating this, what operation I should do? Connect the two. Okay. Then which one goes next? So in a sense, this one and that one does not make any difference because they're symmetric, right? So let's how about doing this one? I remove this one. Then what's the resultant product? I need to tie together this guy, and that guy because they are all the neighbors of that. So I'm going to do this and that, right? All right. Now let's probably just eliminate this one because eliminating this is not going to, it's going to repeat what you just did. Do this one, and what do you get? This one has how many neighbors? It has 1, 2, 3, 4 neighbors, right? So tie them all together. So now you get an idea, right? You can go on and eliminate this one and that one. Eventually, what you get after you eliminate this whole column? You are going to get something in which, basically, somehow everything gets connected, in a single graph, in a single click, right? Essentially, this whole layer will be, the next column will be basically be included in a single click. Right. So that gives you the sense of the intermediate factor that you have to produce when you do either graphical or algebraic elimination. And you can try some other ideas. Maybe you can eliminate this one and see what kind of intermediate entity you are producing. Right. So I think this is probably the best you can do. Right. So now what do you conclude? The complexity of this, the tree width of this graphic model is how much? Is n, basically the number of nodes, in one dimension of this grid, right? So that pretty much gives you an idea about how complex an inference algorithm can be on certain model. Because usually, say this one is deployed on an image, for example, and you have like 255 to 255 type of a moderate-sized image. 255 means the number of pixels, and you define one node for each pixel. That means you have a clique of 250-something nodes, okay? And 2 to the power of that is going to be the size of the table you have to maintain to define the potential function, which is out of question, right? Yeah.
So when you try to eliminate the second column, will that be any different from the first one?
Do it by yourself. This is a graph, right? We're going to save time here. So this could be exercise. Go play with this graph. Do whatever elimination you want. After all, it's just drawing graphs. And you can teach yourself actually how complex that would be, right? All right. So that's the message that, use graph elimination is indeed a good thing. It gives you complexity, kind of estimation, and choosing a good elimination ordering. And today we are going to actually explore the third benefit of having a graph, which is making it a vehicle to do efficient inference. Once you identify the nice order which produce the minimum possible click, and then what's happened next? How can you actually make use out of that piece of knowledge and do an efficient algorithm? Okay, so that's the plan for today. So just to repeat, we have a sequence of entities resultant from elimination. And let me motivate one more time and on one more aspect of why a algorithmic exploration is going to give you more benefit. So here, we pretty much said that, you can basically do this inference, which is to get the the conditional probability of one node given others. You actually did all this elimination until you have this one node left, and then you can now compute the margin node basically based on all the resultant elements, all the resultant factors. So now I ask, what if I change my mind now? I have now, so originally this is my goal, right? And what if now I want to do another inference question where, so I'm interested in this node instead. I want to compute the conditional distribution of E given H. What should we do? You are going to now have to eliminate all the nodes other than G and H, right? Other than G, basically. And what do you eliminate? How do you eliminate? The same thing as we did before, right? We just move one node away, tie their parents and all that kind of thing. And well, in this case, you are going to reproduce some of the elements in here as well, right? For example, you may imagine that, now I'm going to, instead of passing all the messages which represent the intermediate factors defined on the elimination clique, sending them to here, now they need to be gathered in here, okay? And just by inspection or a good intuition, you will notice that, well, the message are sending here and the message sending to here may be different, may or may not be different. They could be different because even though they come out of the same clique, they go to different neighbors. But how about this one and this one? Even if you collect information from here, they still need to go through this path. Therefore, these two messages will be reused, right? So now you can imagine if I want to have a probabilistic database which allows me to answer queries of every node in the graphical model, chances are many of these messages I produce here will be reused just to be sent in some other way and combined with some other messages, right? So how about we just, and also you can imagine, you can see that once I establish this, graph of trees or trees of a graph of cliques, in particular in here we have a tree of cliques, then on every edge of this tree of cliques, there are only two ways of sending message, right? One is go that direction, the other is go this direction. How about we pre-compute all these potentials, right? That's another idea. So you can actually pre-compute this and store them, and then at the end of the day, when you want to do any probabilistic query, you may just be able to look into the database of all these pre-computed clique functions or factors, and then do a quick kind of summarization of the statistic and get your query answered. Right? So that's the idea about doing inference instead of just elimination, because elimination basically gets you answering one query, but doing inference may allow you to answer multiple queries without an explosion of the cost. Okay, so we're going to now get this idea more formally.
What if you want to ask more complex queries, like conditioning on more variables?
Mm-hmm.
Do you have to then build another graph and then with different heats and then compute on those?
You don't have to. You will see that, for example, if you want to answer two queries and together, these two, they become the same clique, and then you basically see message coming into this bigger subset of nodes. It's still a local operation, right? Basically, you can, of course, in the worst case, you want to compute a conditional probability of this one and that one together. Well, that's intrinsically hard, and you cannot save yourself. Then you return to the original case of, right? But most of the queries are simpler, right? And again, here we are not trying to give us a hard time. We are trying to solve the real engineering problem, and therefore, in HMM, for example, we actually know what kind of states people usually like to query people like to answer. Therefore, such algorithm can still be useful. They are not necessarily always solving you the worst case scenario, but they can be very efficient on average scenario or best case scenario. Okay. All right. So before we carry out that inference algorithm, we're going to establish some canonical vehicle, that actually on which this algorithm can be conducted. First, we are going to single out some special class of graphic models known as tree models. Okay, they have some special property which go particularly nice with message passing and later on called belief propagation. So we have 3 types of trees, and their definition is in here. And there are some, first of all, what defines a tree, if you recall? So in the undirected graph, the definition is that there is always a unique path between any pair of nodes. Okay, and in here, same thing. And in addition, you can also say every node had only one parent at most, other than the root. Okay, and this particular concept that a unique path is connecting any pair of nodes is very, very important down the road in establishing the correctness of our algorithm. So bear this in mind. A polytree is a little bit more complicated, and we're going to revisit this concept later on. Okay. All right. And now I need to do another step of reduction. We have these 2 trees here, which appear to be requiring 2 different types of treatment. But in fact, they do not. Okay, they can be unified at least algorithmically by the following definition. So we're going to, here is the joint distribution defined on, say, an undirected tree, because it is undirected, therefore it is a Markov random field, therefore their joint is defined by products, a product of potentials, okay, edge potential and nodal potential, up to a normalization constant. And by the way, here we only have edge and no potential. There are no other clique potential because in the tree, the best clique is the edge clique. And then on the directed tree, we seem to have this Bayesian network definition, right, which appear to be different from here. But if you are willing to accept a equivalence where I call this a margin, a clique, and I call this another type of clique, then we actually have a pretty unified definition of joint probability on trees, regardless it is directed or not. Okay, so we're going to stick with this particular definition of the joint likelihood. And now let's record the elimination, okay, on a tree we see so far. We're going to basically choose a ordering first, and the ordering usually depends on the topology of the entire graph and also where your query is. You need to leave your query the last to be eliminated, right? And then you place potential on the list, and you are going to eliminate node one by one, and each time by removing all the potentials containing the node to be removed through a sum product operation. And then we are going to refill the active list of factors with that newly generated intermediate factors. Okay? So that's basically elimination algorithm in a nutshell. And graphically, let's look at this. It is happening like that, right? So we have a tree, and this is our query. And then a natural ordering is what? Is to peel from the bottom to the top, right? Certainly, you can choose to eliminate this one first. It's kind of odd, right? And you can actually even suffer computational problems because eliminating one creates a 3 clique, and you need to deal with that later, which has more trouble to go. All right, and then here I'm going to introduce this definition called the message, okay, which is our old friend of that intermediate factors that we produced by some product operation. And the way I define that is the following. The message has an argument, okay, which is the resultant variables that is defined on. It is a function of this variable. Basically, it means the variable that is not eliminated. And then I and j correspond to the 2 indices. One is the source, okay, which is actually j is the source, which is the variable to be eliminated. And I is the remaining variable, which actually also can be understood as the receiver of this message. Okay, and they are defined by in a very intuitive way. So maybe I should draw a graph here. I have I have a j. And suppose I'm going to eliminate this guy. Then I'm going to basically also collect all the messages coming from other places into this j. Okay, these are basically those guys. Okay, these are the ones that are neighborhood of node j except I. Okay, I is the one to be sent this message to. And then here are the potential functions that contains the variable j, okay, xj and xij. So that basically defines the sum product operation and the message. And so we're going to reuse this concept, on and on. Okay, so establish first the elimination ordering by putting arrows there. By the way, this arrow does not mean it is becoming a Bayesian network. It is denoting the ordering of my elimination. So I'm going to eliminate this one first and generate this message. And this message, by definition, is computed in that way. Okay, and once I generate that, eliminate that, I record this message, and then I have one node eliminated, right? And I can do this. I compute this message, and therefore this guy got eliminated. And then this guy, remember this guy now actually, their descendants are lost, but there are two messages now from here, right? I think k to j and maybe I to j, something like that. Therefore, we can use this definition to define the message coming out of here to that, right? And that's here, okay? And after that, we eliminate this and so on. And at the end of the day, after eliminate everything, I have in my active list of potentials only factors. That is a function of xf. And then I can ask any queries. If I want to compute a marginal of xf, I'm going to now just multiply all the remaining potentials or messages containing f and then normalize it. Right? Someone may ask, what if I want p of xf given some other evidence? Well, that's very easy as well, because if you do have evidence, in the very beginning, we will define this whole list of active potentials. You're going to multiply that evidence potential there as well. Therefore, the message will already contain that active potentials, or evidence potentials. Okay? So this is elimination. And the good thing is that it is reducing the computer complexity now to a polynomial one. But the bad thing is that somehow, at least visually, after you eliminate, you are having this only thing left. You lose the whole picture of the original model now. You don't know what the original model was. So how about we just record it? Okay, we just keep this graph and record all these messages in terms of where they are coming from, how they are computed, and store them. Okay, so that's actually one way of restoring the computational process of elimination. And people give it a name called message passing. This is like passing the message on the tree rather than eliminating nodes on the tree. The benefit is that you keep the original structure intact. You can still see what's going on. In case you want to reuse the message, you now have a way to actually retrieve it. Okay? All right. So this is now from elimination to message passing. These two things are equivalent on trees. Okay. Now let's revisit the protocol of message passing a little bit more closely to see how they actually address real inference queries. Okay? So now suppose I want to compute a marginal of x. We are pretty clear how it should happen, right? We're going to now generate this message, that message, send it here. We're done. Okay? And then suppose we're going to now compute another query here. What should we do? It is in the middle. We're going to obviously do this and do that and do that, right? So out of these three messages, which one should we compute anew after answering my first query? Only this one, right? This one is a new message which we haven't seen before. But these two messages are actually already computed, so we don't have to do it, right? And three, okay, here. In this case, okay, this message is done already. that message also will head it, right? We only need to compute this new message. All right. So that's pretty much, I hope what you get home already. How many messages we have generated in total so far?
6.
The most we can do is to generate 6 messages, each one, to appear on every node on each direction, right? And then after I generate these 3 messages, I can probably claim that you can ask any query. All I need to do is to multiply whatever appropriate messages and potential together, get them normalized. I answer your query already, right? So this is another step of reduction. You now can see that originally my computation of elimination is, by the way, is already quite inexpensive. It is polynomial instead of exponential, but I need to do it n times because I have n nodes in the graph for the simplest possible query. But with the procedure I just talked about, we actually can do it in 2 times c times because that's all the number of messages I have to compute, right? So that's another step of reduction. Okay, you have a question over there?
What if the x2 is the parent of what if x2 is the parent of x3 and x4 are the parent of x2 in a directed graph?
I already turned them into the undirected one already. Here we're only dealing with undirected graphic models, and they are the same because when you define a directed graphic model, it's basically defined on conditional likelihood. I turn them into the form of a conditional distribution. If, for example, I think what you are asking is this: what if I have this x3 and x4, and I have a p of x2 given x3, x4, right? Well, very simple. That becomes a potential of 3 nodes. Then basically what you have is this guy and this guy. Here I have 3, x4. Very, very flexible. Basically, the potential defines the basic unit of the graph vertices. Okay? Other questions? Good. So we have now our algorithm. Okay, I just repeat. It is a 2-pass algorithm. Every time you are going to pick a order first, and maybe it's a tree, so order is trivial. You just pick any one node, hang it. Okay, then everything basically hanging away from the node will be sending messages up to the node, and then you push it back, okay, like this. Okay, so here I put a summary of the algorithm. It's called sum product, and again, you have evidence being taken care of, and then you do 2 steps. One is called collect, the other is called distribute, and after that, you have everything, okay, on the graph. Okay, that's called a sum product algorithm. Any questions so far? And there is a twist here. You may wonder, shall I actually just go this sequential fashion, a synchronous fashion, where I'm going to pick one order and then send one message after another and so on? Well, the truth is that you don't have to, okay? You can actually go asynchronous like this, okay? And totally actually operate autonomously. The rule is the following. Suppose I'm a node sitting here, and I received every message coming into me except one. Okay, once that happens, I don't care what's happening in the rest of the graph. I'm going to compute a message and send to that node. Okay, this one does not have to be synchronized. Okay, and that's another way of scale up a distributed fashion of message passing. Okay, it's asynchronous, but still guarantee correctness as long as you stick to this rule that I'm going to wait until all but one message is coming and then send to the next node. All right, so this is our first algorithm, and the correctness is established almost by definition. Because what we did just now in defining the message, okay, and in sending the message already guarantee us to reach the correct marginal distribution of any node in the graph. Okay, and here you'll notice that there is this one notion I didn't really play a big deal on, which is between every node there is one pass of sending the message. Okay, And that's why so far we haven't received any problems yet. Yeah.
So we said that we'll wait unless we get messages from all the edges
Mm-hmm.
and pass it on to one.
Mm-hmm.
But in some of the slides, somewhere in distribute, it was sending the message in more than one edges together. One node was sending the messages on more than one edge.
That's a little bit misleading. Okay, yeah, it should be more like the procedure I just talked about. Yeah. In fact, in the real implementation, that's not a big deal because if you only want to send strictly 2 paths, that's the rule I just mentioned. But in many cases, you just keep sending until converging, until the results are converging. Then it doesn't matter; they will be self-correcting as well. That's the implementational aspects of that. Yeah, but we're going to study the algorithm actually deeper down the road in terms of what actually optimization function it is trying to solve. But that's going to be later lectures. Yeah.
So while implementing, you just wait. You don't know where you'll send. You just wait. Whatever edge is remaining, you send it on that edge.
Yeah. You basically look at your neighborhood and wait for your message. Yeah. And you can imagine, obviously, that in the graph, the peripheral, the leaf nodes will be doing the first because they don't need to wait any message before they can send one, right? All right, so now let me ask this very challenging. This is the first challenging question in this lecture. What if I have a non-tree? Okay, let me define a non-tree like this. And I want to slow down a little bit and be very strict about that. X1, okay, X2, and X3 and X4, okay? And obviously, the joint probability of X1 up to X4 is defined by only the marginal, the nodal and the edge potential. So it will be Z times these are the singleton potential, and also X1. Actually, I shouldn't put P. I should put the factor here. Sorry. Okay. X2, and let me simplify that a little bit. Y4, 4, 3, and 5, 2, 3. Okay. I have this distribution. And now you can also do message passing, right? You can probably do, say, maybe, okay, let's say I want to do this one, do the inference of this one. And the message passing will be, this is one way of message passing, right? And now you can actually compute what is the marginal probability of X. I will start this, and maybe you should go home and work out the details. In fact, the scriber, I gave you this extra task of working out the details and give you the starting point. So I have P of X1. That's my query. It's going to be proportional to what? Let's just learn this exercise by heart. It's going to be proportional to all the potentials and messages relevant to X1, right? Therefore, it must contain phi of X1, right? And it also should contain message from 4 to 1, right? It also should contain message of 2 to 1, right? Is that correct? Okay. So now, we need to cyclically expand this because we don't have that. Eventually, we need to go back and remove all this n because now we are trying to check the result of this as a function of all these original definitions, right? So we're going to actually do something a little bit more. Of course, need to be normalized. So X1 is here already. What is my M4 to 1 by definition? Let's put a bracket here. What is M4 to 1? This message, basically. it should be 5, 4, and 5. Okay, it also has to have a 5, 4, 1, right? Right? This edge potential should be there, right? And also a m of 3 to 4, right? And then we should have a summation here over what? 4. Okay, put a 4 here. And then I basically need to copy, actually m, this one. What about that? It should have a sum over 2 of phi 2, right? And also phi 2 to 1, right? Does it have other messages? No, because this is a starting point of message. There is no message coming into here at all, right? So we are going to have that piece here. All right, so this is a little bit mysterious, and then let's do another expansion because this message is not known yet. Okay, so let's copy that x1 and put a sum of 4 here, and 5, 4, and 5, 4, 1, and now it is this guy. We need to expand. Message from 3 to 4. What is the form of that? It has to be a summation over 3, right? And it should contain what? Phi 3, phi 3, 4, and what else? M 2, 3, right? And then we also copy this part. Okay, so it's really messy. And then the scriber should continue one more step here to take care of this message, which is the last term to be defined, okay, in terms of all my factors here. That finishes you the definition of this guy, okay? Okay, why I'm doing this? Well, now I'm going to show you another thing, which I changed the color. How about I'm going to say change my message passing direction. Okay, so I'm going to now compute my P of x1. Okay, using the messages generated from the blue plan instead of the red plan. Okay. And the first step will be the same. It will be phi 1, m4 1, and m2 1. But now, going to the second step, you should help me to get it correct. Okay, expand the same way as we do here. Okay, and up to the bottom, and I want you to go home and compare whether these two are the same or not. Okay, and just to pre-announce the message, you will find, hopefully not too much to your surprise, that the same actually query gets 2 different answers due to my different way of passing messages. Okay, and the crucial problem here is because I have 2 ways of passing messages, and there is no way of guarantee these 2 ways are consistent. Okay, and that's the intrinsic problem of a non-tree. Okay, and that's why now you should appreciate why tree is good. On the tree, you are guaranteed to have only 1 way of passing messages. Therefore, don't run into this inconsistency. Okay, all right. So that's the important message you take home. Belief propagation or message passing is only valid, guaranteed to be valid on tree, and if it is non-tree, it is going to generate inconsistency. All right? All right, so now what do you do? Shall we say that we are going to only work with tree and forget about non-trees? Or we actually find some ways to deal with non-trees, hopefully using the intuition we got from trees. Right. So I suggest you one idea. how about we turn the non-trees into the trees? Okay, so that's hopefully introduce a few more devices and see how we can do that. So here I have a model. Okay, I want to introduce this concept called factor graph. Okay, in which I'm going to produce a factor for each of the potentials. Okay, it is actually the potentials. And then I'm going to create a graph which has two types of node. Okay, there are the factor nodes, which is super nodes, okay, corresponding to every potential you use. A potential could be just a potential or this local conditional probability. And then it's going to have an undirected edge connect to every member variables in the clique. Therefore, you can see this FC here has membership for 1, 2, 3. Therefore, it has neighbor 1, 2, 3. Okay, so that's just called a factor graph. Okay, first step. And let's give an example. So here is a triangle. It's a 3-node graphical model, has cycles. Okay, and you can see there are 2 ways of sending messages, right? You can send this way or that way. But suppose it is defined with these kind of potential functions. Okay, these are only 2 kind of edge potentials. And then we're going to turn the graph like this, okay, which is still a ring. That's a factor graph. Another way is to define a super kind of factor. Okay, this is a factor with 3 components. And you don't have to ask me how these 3 components look like. They could be just this. I just want to treat them together. Or they could be a new table, okay, with 3 entries and rebuilt out of the blue. Okay, but the interesting thing is that the factor graph of this is like that. Okay, it is a star instead of a ring. And so this is a special case of a tree, and that is not a tree, right? So that's the idea. We're going to use this notion called factor tree to actually create a new vehicle or data structure on which your graphical model can be represented as a factor tree, and on which message passing can happen on this graph instead of the original graphical models. Okay. For example, here we have a factor tree, and so we have the factor tree, and we're going to define message passing on factor tree, using the following operation. Here, in fact, this is unnecessary, but just for the clarity of the concept, I'm going to asymmetrize the 2 types of nodes. Okay, so here we first define messages from the factor nodes into the variable nodes. Okay, and they are defined as product of all the messages, okay, containing this particular node. Okay, they're going to multiply together. And then they're going to be sent there. Actually, this is just by definition the potential, the local marginal of this particular node. Okay, and they are going to be equal to a multiplication of all the messages sent from different factors to this node. And then we're going to also, and also that creates the message coming out of the variable node as well. Okay, the variable node is going to be, the message from the variable node to the factors is defined by this, okay, except a particular factor which is the receiver of this message. Clear about that? Okay, and then here we define also the message from the factors, okay, to a variable. And same thing, they're going to be composed by multiplying all the messages coming from each of the variables in here, plus the potential functions defined on this factor, which is this guy. Okay, and then we're going to sum over all the variables, okay, in this big product, except the node that is receiving this variable or this message. Okay, these 2 operations are actually the same. but I made them symmetric so that you can see, a slight difference in asymmetry in the variable nodes and the factor nodes. Okay. In here, there isn't a marginalization step because there is no extra variable to be marginalized over. Okay. But in here, because this factor is bigger than this particular node, there are extra nodes that I don't need, therefore they need to be marginalized. Okay. So we're going to define this message passing operation, and then we basically can come up with a algorithm, the BP algorithm, the belief propagation algorithm on the factor trees, which is first we have the original graphical model. We turn them into a factor tree by explicitly introducing factor nodes and the variable nodes, and we're going to do message passing as we did before, because this is always a tree. Okay, and due to the guarantee of correctness of message passing on trees, message passing on this tree is also correct. Okay. So what's the benefit of that, of this operation? The operation is that, the benefit is that factor tree is broader than tree graphical model. You can turn a non-tree graphical model into a factored tree, and then you can still run message passing on that without running into problems. Right. So here I give you an example. For example, this guy, it is not a tree, right? And you may run into cyclic thing here, and by the example I did before, you can actually cook up a scenario where the message passing algorithm directly on edges will be wrong, right? But now, if you are willing to create a factor out of this whole thing and define a factor in here, then you turn this graphic model now into a factor tree, and then you can run your message passing algorithm, okay, without any problem. And polytree, okay, and actually one student just mentioned already, right? Here, running on the edge isn't necessarily a good idea because my potential is usually this whole thing due to the definition of the conditional probability. Same thing, I can define a factor tree on that, in which the factor potential is going to be corresponding to the 3-node conditional probability distribution. Okay, then I still have a factor tree. All right, so I think I already said enough about the Y factor tree. It is to make use of the tree topology to carry the message passing procedure without risking inconsistency caused by multiple passes between any entity, any pair of entities in the tree.
What's the computational tractability of converting an arbitrary graph into a factor graph in terms of the complexity structure?
Good question. It is bottlenecked at the biggest factor you have to encode in this graph, right? For example, if you look at the Ising model I just talked about, what could be a factor tree of that one?
Sorry, which one?
The Ising model, the grid model I just talked about. If you were to create a factor tree, what are you going to do?
Put nodes in the factors in the cavities.
It would become a star-shaped thing with a single factor.
But that's a factor graph. It is not going to be a factor tree, right? If I'm asking you to create a factor tree, how are you going to create? The best possible factor tree is like what?
The star shape is a tree, right?
Oh, you want to put a star shape? Okay, that's going to be, then the heart is going to be huge.
Yeah.
It's not the, yeah, it is a possible factor tree, but I don't like that tree at all. It's probably too much. It's probably going to contain the entire graphic model as the center, right? So what could be a still okay, even though possibly intractable but better factor tree for an Ising model? Yeah, a colon or row type of reduction or abstraction. I can basically call this a giant node. This is a giant node, another giant node, and then I connect them just like this, right? Become a chain. It's a tree, but the node in the tree in the chain is the whole slice of the model. That's the best you can do, in fact. Okay, and now you can have a sense. You really cannot make the really hard problem simpler, if it is really intrinsically hard. Otherwise, there is no NP problem. You can basically do all this kind of reduction. There are still difficult problems, but at least you know why it is difficult. It is now apparent that you have the bottleneck. But for some problems like this, you really can get it simpler, right? If you are willing to pay a slight cost in reducing the cyclic graph into an acyclic one, you can do what I did just suggested. All right, and I have 2 more slides which I'm going to skip, which is called the max product algorithm. You go home and read Jordan chapter, and it's going to be, it was extensively discussed for another operation called, the map operation, the max configuration inference. So for the interest of time, I'm not going to cover that. So in summary, not the end of the lecture yet, but summary of where we are so far, we have now a sum product algorithm which can help to compute singleton marginals on trees, polytrees, and other tree-like graphs. And we also have the map equivalent of that. Okay, that's what we're so far.
So what's the states of the fact?
What's the
states?
The states, what do you?
Like say the variables in the graph may be discrete, so maybe x equals to 1 or 2.
Yeah.
What about the states for vectors?
For, I don't understand your question.
So in the vector graph, you create some new nodes.
Yeah. Here I haven't seen say anything about the state configuration. It could be generic, right? When I say a potential function on the vector, it could be any potential functions. It could be discrete. It could be even continuous. It could be a table. Anything.
So it's just a variable for getting messages and passing values.
Yeah. What is a message? Okay. Message is basically a score on every state or on every collection of states. So that's essentially what you want at the end of the day. States, what is a state? States is actually a key to a query. It's a query into some database. Say x equals to 1, then what? Right? So then what is actually what you are passing. It's the message. Right? Any other questions? Yeah.
Can we go back a few slides, please?
All right. Which slides?
I think you have 4 nodes for a square.
Oh, okay. That's a challenging one. By the way, we can trade off between revisiting this and taking more stories.
So are you suggesting that for different strategy, for different start points, we can end up with different values for the same
Yeah.
m for with the
Yeah,
technical
yeah.
subset?
Yeah, that suggests it's a wrong algorithm base. That's what I'm trying to say.
Yeah, it's weird, I think.
Yeah, it's weird, right? So it is wrong. That means that the belief propagation algorithm is not going to solve your all problems. It's going to solve you only correctly a problem on the tree, not on such a thing. Okay, and oddly, if I in a way would talk about a history in the future about approximate inference, in graph models, people actually did this for large graph because they have no other options. Okay, then they give it a nice name called loopy belief propagation, because it is loopy. And then they end up with a situation where either the whole thing is never converging, it's cyclic, or it is converging sometime. And magically, when it is converging, they find the results are actually quite correct. Okay, so we're going to actually study why that's happening down the road with some more mathematical muscles. Okay. All right, so any other question? Yeah. You're turning the page is quite time-consuming, so we can hopefully,
Okay.
Yeah.
When you have a graph that is a non-tree and you convert, say, you take 3 variables and put it as one variable. In my understanding, when you can use messages for marginalization, for example. Right?
Yes.
So what if you want the marginalization of one of the variables to have been converted into one variable? Is it still possible to get it?
Yeah, I mean, it is basically getting you a marginal on say this factor tree unit, right? Basically, you are going to get a marginal on every of this unit.
Right, but then, for example, x2 might have been previously like 3 variables. Right?
Yeah, the definition is here already. It is going to be recovered like this. Just take a rule of thumb. Once you finish all this whole thing, you want to do query, you just look into your database of all the factors and just grab every component that contains this one, your argument or your query in that term, and then multiply them together. That's the rule of thumb. So there isn't anything sophisticated. Grab every term. Right? So variable index is a query, is a key, and the variable state is the other key to get you the answer in the end. Right? Yeah.
Can we go back to the message passing on a factor tree?
Okay. This one, this is message passing on the tree.
The message passing on a factor tree.
Do you have a slice
when
number?
you calculate the message from variables to factors, you are using the values of the message from factors to variables.
Mm-hmm.
But when you are, how can you calculate this message from factors to variables? Because when you calculate this one, you using the values from the variables to the factors. So it's like a circle. So how you solve this problem?
You just started by unity, by 1 or some random number. It will self-correct.
It will self-correct.
Yeah.
So it's like when you
okay, let's do this. When you start, this is what I call to be the intermediate step. When you see message already, if you don't have message, the message is 1. Remember when we do the elimination? How do you start the bottom message, right? It should start somewhere, so it is not receiving anything yet. Right? You have this collect and distribute 2 phase, and one of these phase is going to base on nothing, right? And then you go back and send message back, right? All right. Okay, I do want to go forward. I have another 20 minutes, and I have a lot of new material, a lot more advanced material to cover. I hope we can cover as much as we can, but let's see how much we can do. That's actually more useful. So now we are going to answer this question about general graphic models, right? Yeah, so we know that for non-trees, we cannot guarantee message passing, and we have to build a factor tree and so on and so forth. And building a factor tree is not necessarily very trivial, if you remember, if you see, right? For example, we already ran into the problem of starting from the heart and get the easy model factor tree, which contain the whole thing as a single node and so on. So how to actually get a good strategy of building the factor tree. And also, not all factor trees are even correct. Okay, there are some factor trees which actually are incorrect, which I'm going to show you in a second. So we're going to touch bases on this junction tree algorithm in the next 20 minutes and maybe the early part of next lecture. I have mixed feeling. Many people stop covering junction tree for graphical models, and but some other people will spend like 3 lectures or 4 on junction tree because it is very complicated. Such algorithm is actually not in active use these days in the community because it is really very obsolete and complicated. But I want to use it as a vehicle to understand the principles behind exact and approximate inference. Okay, so whether you can implement the algorithm or not is not very important in this lecture, but please do pay attention to the fundamental design principles, okay, and the statistical basis for that. So again, just a reminder, here we have a entity called the elimination cliques, okay, and these cliques are the building block of a tree, okay. If they actually fall into a tree, then we actually can run message passing on the tree without a risk of being incorrect, right? So how can we actually build such a tree, okay? And graph elimination is one thing, but it's kind of tricky, right? You eliminate the graph, a node, and you connect something, and then you use another piece of paper to somehow document what has been produced, because otherwise you don't actually see a part of the graph already. It's been eliminated. So it's kind of odd. So we're going to actually come up with a more kind of systematic and implementable scheme for such process. And we're going to use a few new concepts. First, we use a concept to unify, again, this 2 type of graphical model. And everybody should remember now what is a moral graph, right? Moral graph is a graph where the parents of the nodes has to be married. Although I don't know actually how 3 people can marry if I have 3 parents, but just imagine they can pairwisely married. Okay, so we are going to first turn a graph into a moral graph, and on which the potential is defined by whatever originally was defined on those nodes as a local conditional. And then we are going to stick with the moral graph as our starting kind of platform. Okay, and here, of course, you should understand the potential functions can correspond to very different statistical definitions. Okay, but you can imagine, at least symbolically, they correspond to a table over the argument random variables. Okay, with some numbers filled into the table. Okay, all right. So moral graph, and the clique tree shall be built on top of the moral graphs. Okay, let's begin with a simple scenario. So here, this is a moral graph, and we built, let's say we just use a max clique. Okay, and then we have such 3 cliques, and that gave me such 3 cliques, and this is a tree, right? This is a clique tree. Okay, and here I'm not resorting to the factor graph just for simplicity, because this is already good enough to carry out message passing directly. And here I'm going to introduce another concept. Okay, I want to re-engineer this whole thing a little bit, and here I define the original clique potential, okay, and also something called a separator potential, Fs, which is taking care of the intersection between 2 adjacent nodes. Okay, and you will see a reason why I do that. I make that a big deal. So as a result, I have such a thing. Okay. Okay, so the first utility of defining a separator clique is to now enabling you to directly make use of clique potential to define marginal distributions. For example, if you now do some massage, okay, originally, you probably realize that every potential either corresponds to a conditional or a marginal. But with the definition of clique potentials, you can now safely claim that every potential corresponds to a marginal of subset of nodes. Okay, and they are arranged in this way. Basically, the joint distribution now can be written as on the denominator product of full clique potentials, which correspond to clique marginals, and then in the denominator, and we have the clique potentials on the separator cliques. Okay, so that's the first thing. By definition, we have this correspondence between clique marginal and the joint distribution. All right, and now again, how can we use this to come up with a message passing algorithm, or why it is useful? Well, it is useful, first of all, once you actually have a correct estimation of these clique potentials, okay, suppose we have all that already, then you are going to be able to turn the probabilistic inference queries, like asking potential function, asking conditionals, asking marginals, and all that, into a local operation, okay, and only on those potential functions that contains the argument random variable. For example, here, you know, even though it has evidence already, you don't have to do that after you do message passing. You only look for a potential that contains this node 1, and then you're going to sum over the other 2. You wonder why, what does this evidence, how do they influence on the potential? Well, that's the story we're going to talk about in a second. Notice that in this graph, if I don't shade this node, then I already have the potential functions by definition, right? I already have that. But once we introduce a evidence or some other perturbation on the model, what's going to happen? Okay. So what's going to happen is that we're going to use a message passing procedure, on the tree, to recalibrate all the local potentials so that it becomes a new probabilistic database where all the evidence and information are taken care of, and you can still do this kind of local inferences. Okay, all right. And here is the local inference procedure in a nutshell. First of all, we need to define some important properties of these local potentials. I have the psi and phi, on the sets, and they must satisfy what we call a local consistency property. They need to actually lead to correct normalization or marginalization. So this is a very important and a strong constraint, which says that I have these two clique potentials, okay, or clique marginals, and each of them contain the S as a subset, and therefore I have now two ways of computing the marginal distribution of S, right? And these two ways must give me the same result. That's basically an implicit constraint you have on these two different potentials. Okay. And so now imagine I need to do message passing and compute all these local marginals. And what is a procedure that ensure me to get this consistency? That's actually also lie in the heart of the issue we just talked about. There could be a risk of being inconsistent, if you don't do the procedure correctly when you look at the marginal on a single random variable, right? So here I first present a procedure that eliminates such a risk, and then let's see why that's happening. So I claim that you want to do this procedure. Suppose that you have these three potential in your starting point, which is obtained just by definition because you need to define a graphic model in the first place, right? And then your graphic model is now used to answer query. Answer query means that I see some evidence, I see some nodes to be observed or being in certain configuration. I'm going to ask a query conditioning on that. Then how it should be done? It should be done in the following way. I'm going to multiply this evidence potential, okay, into my original definition of potential. For example, here I may actually multiply some delta E, something like that. And therefore, I had a new potential right in here. So once this potential is becoming a new version, for example, now I have psi of V into psi star of V. It is a new definition due to introduction of evidence, maybe. I'm going to now recompute this separated potential, okay, just by marginalize the thing that is not included here. And then I'm going to go forward and recalibrate this potential function, okay? Even though it is not directly influenced by the evidence in here, I still need to recalibrate by basically multiplying the original potential with the ratio of the new separated potential versus the older potential, okay? And then this one gets a new one. What should happen next? Remember, our message passing algorithm is always a two-pass algorithm. It should actually go there and come back. Therefore, I'm going to recalibrate this S again, okay, by doing another step of marginalization. And then I'm going to recalibrate this one using the new ratio of new and the older version of the clique potential multiplied by its original value. See that? So that's basically the life span of a new evidence. Some evidence comes in and contributes a delta, and then that turns this one into this star, and then it goes to this to turn this into a star, and then go here, turn this into a star, and then go back into this double star, and get this back into a double star. Okay, now you have the new set of potentials, which are respecting these local constraints. And in fact, they have a number of other identities that you can prove. This one and this one. Both the local marginal and the global joint distribution is invariant, okay, due to actually this procedure. Okay? Okay, so this is a new message passing algorithm which actually happens on the trees, okay, on the click trees, okay. And later on, we're going to revisit this very abstract form in some explicit kind of example, such as HMM and other things. And you will see they actually really are instances of this very generic idea. But now let's take care of another issue that we just actually ran into already. So we have this message passing algorithm. Okay, this seems to be doing okay. Once you have a click tree, and you can now define the probability propagation, and you seem to have also the local and the global consistency guarantee. Everything looks okay. Okay, but are we actually right here? Are we actually all done, or there are still some tiny issues not discussed? Right. Okay. So originally, when we say this issue, we talked about the issue being having two ways of sending messages, and that creates some inconsistency. And now we say we have an idea of turning the graph, turning the non-tree graph into a tree, and then message passing is to get everything correct. But there is one little thing we actually still are not tying the loop yet, which is how to create, or are every tree correct, or there could be some trees which are incorrect. Okay, so here I have this particular tree turned from this graph. Okay, and in this case, you see something a little bit alarming. Can someone actually point it out? So I have this question here. Here is a random variable. Here is a random variable. Okay, and they are in two different potentials. So imagine I define now in the click potentials. They will be here and here. Okay, and this potential will be computed using the procedure I did before, which will ensure some local consistency. Local consistency means that, say, if I have an A here, I have an A here, they're going to lead to the same marginal, okay, using each different potentials. But strangely, I have a C here and here, which is not subject to such constraint, right? Because they are not adjacent to each other. So I still have two ways of computing the P of C, okay, from this click and from that click. So now I ask, do I have a mechanism to ensure that they are consistent? Any comment? Okay, at least you cannot be so brave to say, I'm guaranteeing you that it is going to correct. Because in my procedure in here, there is no such a device to actually make sure that they are going to be always calibrated together, right? So that's actually indeed a problem, okay? And we actually say that this particular tree is flawed, okay? It lacks a very important property with many different names. The property is known as something called a junction tree property, or something also called a running intersection property, or something also called a triangulation property. All say the same thing, which means that somehow there are nodes shared by two different disjoint, two different potentials, but there is no path connecting this potential which contain the same node, so that they don't actually have to satisfy a local consistency constraint. And when they don't have such a constraint, you have no guarantee that they are correct. Okay. So any suggestions on how to correct this problem? How can we avoid such a lack of local consistency for seemingly, disjoint potential functions? Any ideas? So let me propose one. How about we define the potential a little bit differently. We basically define A, D, B, something like that. Or maybe I should maybe make it more explicit. Maybe I should say A, B, C, and B, C, D. Okay, and I put a click here. Right. Then this C is indeed subject to my consistency constraint.
These are not cliques, are they?
I basically can call this a clique. I can add an edge here. I'm going to create a clique. Yeah. Remember that when I do adding edge is fine because even in my moralization I'm already adding the edge. Here is about adding more edge. Okay. So just a long story short, there is a step called triangulation. Basically, what is really causing the problem is that this graph is not triangulated. There are loops, in any 4 nodes, which cause you, a potential of creating a scenario like this, or a message passing that is loopy or having multiple paths. But if I do this, I'm going to turn this graph into something called a chordal graph or a triangulated graph, where I'm going to put a chord for any 4 nodes that is not triangulated. Then I'm going to get something like this. Okay, and then I'm going to be able to create a clique tree, which has an important property called the running intersection property. It says that for any pair of potentials, let's say here and here, which contain some kind of nodes in common, then this node must also appear in any of the edges or any of the potentials or cliques that is on the path between these 2 cliques. Yeah.
But you violate the conditional independency of values.
I can validate. No, I don't have to, because the design of the potential functions in my hand, right? I can basically prevent such thing to happen. Remember here, look at I'm not changing, I'm not basically doing the data structure. The distribution, if I'm giving a graphic model, is already given. It is defined already. For example, potential may be defined only on this and that and that and that already, right? Right now, it's really about a data structure generation. I can define a 3 potential just by multiplying these 2 together. That's it. So there is nothing added. It's just a different, smarter way of grouping. So graph in here is not, remember, this is not a graphical model. Okay, junction tree is not a graphic model, or this chordal graph is not a graph. It is just a representation of how message can be generated and grouped. So don't confuse this with a Macquarien field. I'm not changing the model at all in this case. Okay, starting from here, I'm basically creating a vehicle to conduct message passing. Okay, so it is not a graphical model. All right. So this is something called a junction tree. So basically, any engineered or recreated graph with this running intersection property or this triangulation property is known as a junction tree. It is a tree of cliques which satisfy the running intersection, so that when you run message passing on such a tree, it is guaranteed to be correct. Okay, because when you pass any message on the node, it is going to carry those nodes which are supposed to be consistent with some other nodes in the other clique along its message. Therefore, it will be contiguously recalibrated and made sure to consistent. Okay. All right, and I actually asked a few more questions. Okay, for example, how do we triangulate? The complexity of building a junction tree actually depends on how we triangulate. You may get a bad triangulation which can make the whole thing quite complicated. And these are the stories we're not going to cover. That's why I say the whole lecture can take very long if we go through details. But the nutshell is the following. If actually through doing all this, building junction trees, building nice structures, you somehow turn a very difficult arbitrary inference problem into something that is completely manageable, you are violating this NP complete conjecture of inference problem. Okay, so pretty much it means that getting triangulation in the optimal sense is an art which can happen in some graph, not all the graphs. But drawing the graph inspire you sometimes a better strategy over some other strategies. So we're not going to talk about how to construct best junction tree in this lecture, but you can get a sense already, right? By doing some reasonable elimination ordering, you can get a junction tree that is better than others. All right, so this is something I want to pass. And I just flashed at you a junction tree we produced earlier. And then on that, we have basically a way to deploy the same operation we did before. We have the message passing, collect and distribute it. And here every node now is a junction tree click instead of a singleton node. And these are the protocol we just discussed. It has a nice name. It's called I think it's called the Hujin updates. There is another update we're going to discuss in next lecture. Okay. All right. I'm actually pretty good. I'm 5 slides to the end, so we're going to leave the 5 slides for next lecture. See you next week.